All right, and welcome to the lesson 3.1 notes, solving quadratic equations. So we get into, in this lesson, yeah, exactly that, solving quadratic equations. We'll look at basically just different ways to do it, different methods. So you can kind of see from our big ideas, we're looking to, we'll solve by graphing. So we're still graphing. Holy cow, that's been a concept that's been, almost an exclusively chapter 2 was all graphing. Um, we've done, uh, solve quadratic inequalities by graphing. We're going to solve quadratic equations by graphing. So still building on or still using some of those skills from chapter 2. We'll use square roots, factoring. We'll look at how can we apply these to maybe some physics type of situations. So I think let's just get into it. So when we're solving, basically what we're doing, um, there we go. That's what our standard form looks like. We should all know that. Ax squared plus bx plus c. The big thing here, the note on this when we're solving a root, when we hear that word, or usually it'll be in the directions when it says find the root or the roots of an equation, it's asking us to find the solution. Okay, so that's the big takeaway here. Just make sure we add in our notes that a root of a quadratic equation is another name basically for the solution of the equation. Okay, overview is here. The graphing, I mean, this is real basic. We'll break each one down a little bit more specifically, but by graphing, it's that the solutions are my x-intercepts. We want to be equal to 0. That'll be part of what we'll do. Again, we'll add that here in a second. Square roots, this is more what I would call kind of your typical, your traditional algebra. Move everything away from your squared term using traditional, like I said, traditional algebra. And then you finish by taking a square root of each side. Last one is factoring, basically going from standard form, putting something in intercept form, and then solving using the zero product property, which we'll talk about. So let's just go one at a time. Let's solve by graphing here. Here's the basics. Almost always we're going to see a solve by graphing in standard form. All right, that's our ax squared plus bx plus c. We're going to want to be equal to 0. So if we see an equation that's not equal to 0, we'll have to move stuff around. I say here using usual methods. So again, go back to lesson 2.2 where we kind of went into detail on how to graph something in standard form. Our roots, our solutions end up being our x-intercepts. And the last part I put here was just, consider the number of solutions you could potentially have, because, what three things could, what three outcomes could happen when we graph a parabola, right? We know the shape in a standard form is going to be a parabola. We could end up with a graph that ends up crossing my x-axis twice. So we'd have two solutions there because there's two x-intercepts. We could end up with a graph that just touches it once at its vertex, whether it's opening up, down, doesn't matter. And then we could potentially end up with a graph that doesn't cross my x-axis at all. We'd say, for now, let's just say that there's no real solutions. Is technically is what we should say. We can say just no solution. We don't really know the difference right now at this point between real and imaginary solutions. There will be what I've just said, some imaginary solutions, but we got to learn about that still. That'll come up in future lessons. So no solutions in a case like that. All right, let's do it. Two examples going with it. So, yeah, I think there we go. There's a standard form. It's equal to 0. Graph it. So you pretty much treat it like a graph. There's just the follow-up of what are the roots, what are the solutions. All right, so how do we graph something in standard form? We start with the axis of symmetry, which is found by going the opposite of b, which b is -1. So the opposite of that is 1 over 2 times a, which is 1. All right, so we end up with 1 over 2. Axis of symmetry is 0.5 or 1/2. All right, that means half, I've got the x coordinate of my vertex is 0.5, so that's a big value for us. It gets us going. I could put that on my graph, right? My axis of symmetry is halfway in between here. where do we go from there? Well, we got to plug points in. Basically, the rest of this now is plugging points in. Let's finish up our vertex because that's always the kind of the key point we're looking for. I'm going to plug in this 0.5. So 0.5, or this 1/2 squared, minus 1/2 minus 6. All right, so we're treating this. Yeah, so we got 0.25 minus 0.5 minus 6. I'll double check it here. I'm pretty sure I got it, but I want to make sure that I got the right. I got negative 6.25 on my calculator as I was punching that one out. All right, so there's our vertex, negative 6. Not a great vertex, but it is what it is. 0.5 down 1, 2, 3, 4, 5, 6, and just a little bit past. We've seen one similar to this, that the vertex isn't a great point, but because of we get to pick the next points, let's pick nice, clean, whole integers to put in there. So I'm going to jump up to 1, and I'll go down to 0 as my next set of points there. 0 is a nice point for us. We've seen that again with this form. If I plug in a 0 for x here and here, we get that cancel out, and I'm just left with negative 6 for my y-intercept. So that's another nice point for us. So I'm here and here. So here's my thoughts on this one. I think most of us, and I'll probably do it the way that I'm thinking a lot of people would just kind of keep going. We'd go up to 2 as the next nice whole number up, and then the next integer down would be negative 1. So as I go to plug in a 2, we graph it. I'd plug in a 2 here and square. Let's just do the work down here. 2 squared is 4. So I'm going to plug in a 2. I'm going to minus 2, and then we'll subtract 6. So 2 squared is 4, minus 2, minus 6. So 4 minus 2 is 2. 2 minus 6 is negative 4. But here's kind of the issue that we're having right now. Where are we at? 2, negative 4, negative 1, negative 4. 1, 2, 3, 4. Now, in previous lessons, we would say, all right, sweet, we've got a full table. We're good there. I've got some points on my graph. I'm ready to graph this. We would do this. We'd do that. And say, awesome, that's a great graph. And I would agree with you. It's a pretty good graph. Where we got to take this a little, a step further is we got to find the roots and the solutions. Right now, the way I've kind of informally sketched my graph, I'm not quite sure what those x-intercepts are. Right, I would be guessing at this point. So we need a little bit cleaner of a graph. So I'm going to back those off there, hopefully. And I basically have to kind of keep extending my table a little bit. So here's where you, like I said, be strategic. If you saw that it wasn't quite getting there, we weren't going to get to the x-axis yet, you could jump up, right away to maybe 3 and negative 2 and think hey, it's probably going to be closer to there. So I'm kind of extending my table at this point. I'm going beyond what the 5 points I normally ask you to plug in. Let's do it. Let's plug in a 3 here. So if I plug in a 3, I'm going to get 3 squared. I'll just do it. 3 squared is 9. Minus 3 minus 6. So there's my 9 minus 3 is 6. 6 minus 6 is 0. Hopefully, if we're using graphing as one of our methods to solve, 1, 2, I'm just going to plot these points here while I'm talking. Hopefully, if we're using this method, solve by graphing, this should happen, where I end up with some clean points for my x-intercepts. Okay, and that's actually one of the downfalls of solving by graphing. What happens when those x-intercepts aren't nice? They're not clean. They're decimals, irrational numbers potentially. Then our graphing method is somewhat limited. Okay, so there we go. Just finish it. What are my solutions? We would say, what are my roots? X equals, what are those coordinates there? And it's really just the x coordinates. So 3 and negative 2, we said. So almost all of our problems for today will finish with x equals this and this. Many times 2 solutions, but we just saw potentially 1 or 0 solutions. All right, we'll just do another one because it's the video notes. If you're feeling good about it, you can obviously skip ahead. Couple different things going on with this one. I'd look at, the first right off the bat that the equation's not equal to 0. So we've got some options there. I would definitely, you could bring everything to the right side. I'm going to bring everything to the left. So I'm going to subtract a 4x from both sides. I'm going to keep the minus 2, and we're equal to 0. So that's the first thing. Make sure we're equal to 0 if we're not. Some people might see that and want to bring everything to the right side, bring this term over and this term over here. That's totally fine. We're going to end up with similar graphs, but not identical, because the graph that I'm going to make right now is going to open down. How do I know that? Because of that negative right there, right? My graph's going to open down. If you brought everything to the right side, right, this 2x, this would be a positive 2x on the right side. So you'd have a graph that opens up. So we may not have identical graphs, but I can tell you the one thing that would be identical is our x-intercepts. Okay, so don't feel like you always have to bring everything to the left or to the right. Some people would rather work with a positive a value, and that's totally fine. So it's however you want to do it. So I'll just go with what I got boxed up here. So same process now, opposite of b over 2a. So opposite, can we scratch it in right here? X equals the opposite of b, so the opposite of negative 4, over 2 times a, which is negative 2. So 4 over negative 4, which is negative 1. There we go. That's not a bad axis of symmetry. Half my vertex, centers up my table. I like it. So as I go to plug it in now, let's see what happens. We got to get let's get the y coordinates. So negative 2. This one I would definitely probably write out, where it's just, negative 2. All right, I'm plugging in a negative 1. There's just too many negatives, I think, to try to do this in my head. Minus 4 times negative 1 minus 2. So I'm going to square the 1, or I'm sorry, the negative 1. It's going to turn into 1, but then I'm going to multiply it by negative 2. Negative 4 times negative 1 is positive 4, actually, and then I've got this minus 2. So negative 2 plus 4 is 2, and then 2 minus 2 is 0. So it's kind of unique. Like that's negative 1, 0. Where is that? Negative 1, 0. That's my vertex. And we know this is going to open down. So I'm going to finish this, but I know this graph is going to do something like that. I think I have my solution already. I have my root. So I am going to ask that we finish it. I know I could. We'll wait till the end that I could answer this question, x equals. But the other part I'd want to just kind of assess is your ability just to make the graph. So finish the graph. I think I have my solution already. I know I have my solution, my root, but let's finish it. So I don't think it's going to be terrible. If I go up from here, I'm going up to 0 and 1. I'm going to go down to negative 2 and negative 3. 0 is a great point for us because why? I know what if it gets plugged in here, I know what my my y-intercept is negative 2. Negative 2 and negative 2, so 0, negative 2, negative 2. So just one more point to plug in. So just watch it. Again, watch that negative a value 2. 1's getting plugged in here, minus 4 times 1, and then minus that 2. So negative 2, but this time it's minus 4, and then minus 2. So negative 8 it looks like we're going with here. Negative 8. Negative 8. So 1, negative 8. Ooh, gotta count it out. 1, 2, 3, 4, 5, 6, 7, 8. And then 2 this way. There we go. So there's my graph. Finish it. Draw the lines. Connect the points. Last thing, and just don't forget, I guess maybe I should have done it. Where are my x-intercepts? Intercept, in this case, there's only one, would be at negative 1. So there's a look at a graph that only has one x-intercept, so I only end up with one solution. All right. The only one we didn't see would be a graph that, does this. But obviously, we talked about it. If that happens, we're just going to say no solution. So I think that's pretty good for graphing. It's basically graph using our traditional methods. There's just that follow-up of what are your x-intercepts? And those are our solutions, okay? All right, so they're solved by graphing. Sweet, one down. Check it off. What do we got next? Solving algebraically using square roots. So before we actually get to the square roots, we do have to go over some, hopefully this is review for you, but if not, just reviewing what simplest radical form is, because you're going to see, just to kind of preview what this looks like here, it's going to say solve using square roots. It should say, the directions will say solve the equation using square roots, write your answer in simplest radical form when necessary or when possible. So let's talk about what does that mean to be in simplest radical form. Basically, there's a couple things that we're looking for. We don't want to leave any perfect square factors underneath a radical. That's kind of one of the things. There's this like a series of things we got to look for. So we'll go over what does that mean? How do I fix that? We don't want to leave any radicals in the denominator of a fraction. So we shouldn't have a square root in the denominator. So both A and B have that. The other situation that's coming up here, both in both of the part C's, we don't want it, and I don't state it anywhere, but we don't want to leave a fraction underneath there either. Okay, so for both parts C and C, I guess, have that issue where there's a big fraction underneath this radical. We got to fix it. Okay, this is going to get tight on space because it's simplifying purposes. So I might go back and forth here. This will take a little bit of time, but hopefully it's worth it as far as just reviewing some of these properties. So I guess first thing, what the heck is a perfect square factor? Perfect square, just let's talk about that part. A perfect square would be examples would be, one would be a perfect square, but it doesn't help us a ton. We're talking more like 4, 9, 16, 25, etc., 36, 49. Those are perfect squares. And then factors, are multiplied to, if you want to say it like that, numbers that multiply to some other number. So we can't leave those underneath there. So I guess I'll start on here with A, but I'll probably have to, for parts B and C, maybe do them on a separate sheet. We're looking basically to break up this 117 into two numbers that multiply to 117, but I'm hoping I can get one of those numbers to be a perfect square factor. So I'd get my calculator out and start dividing. 117 maybe divided by 4. I probably wouldn't check 4, but just because of the 17, but then I might go 117 divided by 9. I know you can't see me here, but I'm just kind of checking on my calculator. 117 divided by 9. And my calculator says 13. So I can tell that 9 goes in there evenly. So basically this process is I've broken this 117 up into two of its factors, 9 times 13. A property of a square root says you can split this then into two separate square roots and evaluate any that we can do. So we've kind of strategically picked 9 and 13 for the reason that I can evaluate the 9, not the square root of 9 is 3, and then the 13 stays put. So it's 3 times the square root of 13. You don't have to put the dot in there when we see a number in front of a square root. We're assuming that it's multiplication, or that's implied. So that's the process there. That's what the square root of 117 looks like in simplest radical form. All right, maybe we can get B done here. It's a very similar. Obviously, the bigger the numbers get, the more perfect square factors. So if you start, actually 396 does divide by 4, I get 99. But maybe I recognize, or at least I do, that 99 also has 9 times 11. So there's more perfect square factors in there. So I want to kind of keep going. I want to check I want to see if I can find any bigger perfect square factors. So let's check. I'm going to go 396 divided by 16. No, it doesn't work. 396. I know 25 is not going to go in there. Let's jump up to 36. And I actually see that, hey, this can be written as 36 times 11. 36 times 11 is 396. So when I break this up, 36 times the square root of 11, the square root of 36 is 6. The square root of 11 is a square root of 11. There we go. I've put that in simplest radical form. All right. Let's go ahead and do this one. Why not? Maybe there's room here. We can talk through it. I guess if you've already seen those, I could probably erase those if I need some more room. So here's the other situation that we said was no good here is we've got this big old fraction underneath this radical. So the first thing I would look to do here is just to split this. It's another property. It's actually the same property that we talked about. We're allowed to break a big radical up into two smaller radicals, just like that. So I've kind of split that and said, all right, we've solved one problem. I no longer have a fraction underneath. It's just a 60 underneath a radical, and it's a 16 underneath a radical. We've created a different problem. There's a square root in the denominator, right? Well, this one's easy to fix. So that square root of that denominator, the square root of 16 is 4. So that kind of fixed itself. It would just happen to be a very convenient denominator, 16. So I bring over the 60 and I say, that's pretty good. We're fixing problems. I still have this situation of, are there any perfect square factors underneath that radical? So I still have to address that. And I say, yeah, there is. If I do 60 divided by 4, I get 15. So this numerator can be broken up into, just like we did on the previous two, 4 times 15 as two separate radicals, still over 4. Just to note here, sometimes people see this 4 and think I want to square root this again. No. Can't do that. I know we recognize it as being a perfect square, but we've evaluated the square root of 16. It was 4. That's 4. There's no more square root there. So just wanted to mention that. Let's finish this one, at least this part C up. So I've broken that 60 up, 4 times 15. I'm going to do the one that I can do. Can I squeeze it in here? 2 times the square root of 15 over 4. And I'm saying, yes, finally, I've solved all my problems. Can I go through my checklist? No perfect square factors under the radical. There's no fractions under a radical. There's no radicals in the denominator. I'd say we're doing pretty darn good. The last thing I'd tell you is we'd want to reduce anything that we can reduce. So this is just like 2/4. You wouldn't leave a fraction as an answer as 2/4. We all know that means 1/2. So absolutely, I would finish this that same way. I would reduce those and just say my final simplest radical form would be the square root of 15 over 2, right? There's a 1 there, but I wouldn't take off if you wrote that there, but traditionally you wouldn't see that. You would just see it as the square root of 15 over 2. Wow, there's a lot to think about there. So that's where we end up. That's the first kind of part here of putting something in simplest radical form, getting those perfect square factors out from underneath the radical. The second part that we have to be aware of is how do we fix that? So the only thing we really haven't talked about is how to fix that situation where we end up with a square root downstairs in the basement in the denominator. So our method for fixing that, it's called rationalizing a denominator. And with square roots, it's the same process every time. I'm gonna need to multiply both the numerator and the denominator by the same thing. I can't pick and choose and multiply the top by something different than the bottom, because that would change the value of it. So we're deciding on the square root of 7 over 7, which has a value of 1, so I'm not changing anything. But what does that do for us? That puts us up top at 5 times the square root of 7. We kind of just smash them together. They are what they are. The bottom, though, the denominator, gives us the square root of 7 times the square root of 7. If they're both underneath a radical, I can put those together and say, oh, that's the square root of 49, which hopefully we recognize is 7. So it should always work out that way. I can probably bypass this statement and just jump right to here, because we know what's going to happen, that denominator should turn into a perfect square because we're choosing to use that same number. So I would just look to reduce, if I could, if it's possible, the 5 and the 7, but obviously in this case, being both prime numbers, they don't reduce. There's nothing that goes into 5 and 7, so that's one that we would say we're done. B's got a little bit more going on. Let's see if I can kind of section this off here. I'll try to use as much space, but keep it readable. This 18 has got, it's the same initial, maybe, like, hey, there's a square root in the denominator. I got to fix that. There's also some stuff tucked in there. There's a 9 and a 2, right? A 9 is a perfect square. So there's different things I can do. I could go through the same process of just multiply top and bottom by the square root of 18. Some people might want to simplify the denominator first. Maybe let's go down that route. Okay, so I'm going to keep the 10 up top and just say, hey, this denominator is the square root of 9 times the square root of 2. So 10 over 3 square root of 2. So you're asking yourself, well, okay, that's awesome. That's great. It still didn't fix the problem. It'll make our life simpler in the end. Okay, because we fixed one of the problems, that there was a 9 and a 2 tucked into this 18, or there was a 9 in there, but yeah, 9 times 2. I still have this issue of, okay, well, there's still a square root of 2 in the basement here. We got to fix that. So now is where we would look at what we did earlier, or on the previous problem. So I'd look at, all right, let's multiply both numerator and denominator by the same thing. I'll probably try to work over here just to save some space for this last one. What did we say happens on the top? We just smash them together. The square root of 10 times the square root of 2. We haven't done as much with this here, so it's worth reviewing, or at least talking about here. What happens? Maybe we do want to write this one. It's 3 times the square root of 4. That's what happens with this square root of 2 and 2. They get turned into the square root of 4. So maybe in a second step, or a third or fourth, or whatever step we're on here, I kind of write this as 3 times the square root of 4, which is 3 times 2, which ends up being 6. All right, so there's, I think a lot to think about on a problem like this. Similar to what we saw in part B above there, I want to reduce. I want to make sure that I finish the 10 and the 6. They're both divisible by 2. So my last kind of simplified 2 goes in here 5 times, and 2 goes in here 3 times. One thing I think also worth noting is if I kind of look at this step right here, 10, 6, and some people see this too. Hey, those are all divisible by 2. Why don't we divide this by 2 as well? But the problem is we've got a mismatch of formats there. This is just 10 in the numerator. This is just 6. We can reduce stuff that's kind of outside of a square root of a radical, but because the 2 is underneath this radical, it's kind of locked in there, and I can't reduce it. So it just stays put. All right, let's go through this last one. Again, it's video notes, so obviously I understand that you can, if you're feeling decent, you can skip ahead. What are our problems right now? Well, the first thing I see is I've got this 27 over 2, just kind of like the one right above it. Let's split this into the square root of 27 over the square root of 2. All right, so at least we fixed the one problem. No more, there's no fraction underneath the radical. There's different places I could go now because I've created other problems for myself. I've put a square root in the basement in the denominator. I see that 9 times 3 is 27, so I've got that issue to kind of address at some point. It doesn't matter really which one you do. I'm probably just going to, let's fix this denominator. Okay, so I'm going to multiply both top and bottom by the square root of 2, which up top, because they're both underneath, I can actually do the multiplication and make that 54. And then I got the square root of 2 times the square root of 2, which is square root of 4. Going to turn us into 2. So I've solved problem number 2. Here was problem 1. We had the fraction underneath. Problem number 2 was the radical in the denominator. Problem number 3 now is this 54. So we've kind of seen all the pieces here. There's a 9 times 6. 9 times 6 is 54. So kind of last step, hopefully, I'm going to break that numerator up. So here's problem 3. That 54 has got to get broken into 9 times 6. We'll just leave the denominator alone for right now. Let's see what happens. The square root of 9 is 3. The square root of 6 is square root of 6. It's not nice. And my denominator is still 2. I think we're okay. The 3 and the 2 don't reduce. I don't have any more perfect square factors in here. Just the only factors of 6 are 1 and 6 and 3 and 2. So we're good on that. So there we go. There's a fairly actually lengthy review on just properties of square roots and radicals. We'll use those as they come up in some of our using square roots, okay? All right, so let's actually solve some equations using square roots. Here's kind of some general notes. That there's not a ton, but the biggest thing is consider the number of solutions. How many solutions did we end up could we have ended up with when we were solving by graphing? It was 2. Most of the cases, there's going to end up being 2 solutions, but there's potential for 1 solution, and there's potential for no solution, okay? For whatever reason, when we're solving using traditional methods here, people really forget about that we should in most cases end up with 2 solutions. So let's look at some simpler examples here of I might even throw like make this part E and then do a part E, do a fifth one here just to kind of see it. So whatever, let's work our way through it. How do I know when there's 2, 1, or no solution? So let's say throughout the course of solving a problem, I ended up at the last step here would be to square root both sides of the equation. X squared equals 49. So I say I'm looking for 2 numbers basically that multiplied to 49. So I'd square root both sides of the equation. Most people say like, oh, sweet, that's easy. X equals 7. But there's a second answer. X can also be negative 7. What is negative 7 squared? Negative 7 times negative 7. Heck yeah, that's positive 49. So there's an example. I need 2 solutions there. A lot of people forget that second solution. My suggestion is this. whenever we get to this stage of an equation, we're trying to solve it, and I find myself, and I would encourage you to draw the square root. When I find myself drawing a little square root symbol, the first thing I'm going to write down is plus minus, like positive, negative, just to it almost create like a very mechanical approach to it. Hey, I drew a square root. I need a plus minus. And then what is the square root of 49? 7. Because now I've covered my bases, positive 7 and negative 7. So I'm okay if we want to write it like that as well. So there's what two solutions would look like. Any positive number over here. I'm going to do that part E right away. All right, just because it goes along with this. Let's say, and it's going to look very similar. Let's say we get to a spot where it's x squared equals 32. Not much different than we just saw right there. X squared equals 49, x squared equals 32, except what's the difference? Well, obviously it's a different number, but 49 was a perfect square. 32 is not. So what? Doesn't matter. Okay, so when I go to square root this, what did we just say was kind of the suggestion? Automatic. Make it plus minus. That's a plus. 32. Now here's where that simplest radical form would come up, where I'd say, oh shoot, there's a 4 times 8 in there, actually there's 16 times 2. Almost missed that one. So that's how we're going to use that. Okay, so I've got the right value, the positive negative square root of 32, but people kind of see the 16 and the 16 times 2, so 16 times the square root of 2, but most times they forget about the positive negative. So my final answer for this made up part E would be positive negative 4 times the square root of 2. Okay, so a couple different things going on there as far as keeping track of that positive negative, and then having to put something in simplest radical form. Again, don't re-square root this. That seems to be a real common thing that people want to do because they see this 4 and say, hey, shouldn't I square root that again? We don't. We would not do that. All right. Again, there's still two solutions there. There's a positive value and there's a negative, positive, negative. What does it look like to get a no solution? So it's a situation like this that I get to a point where I'm ready to square root, and maybe I say, okay, hey, Mr. Crow said to write this as plus minus, and then I start to hopefully recognize that what is the square root of negative 25? Is it 5 and negative 5? So I maybe check my calculator. I type that into my calculator. The square root of negative 25. The calculator I'm using says domain error. I say, what? And if we take a step back and kind of think about it, like, okay, I need two numbers that multiply together to get negative 25. It's got to be identical, the same number. So 5 and 5 doesn't work because obviously that's 25. Negative 5 times negative 5 is also positive 25. I don't think we can get there. So you're kind of like, well, what? This is the example where we would say there's no solution. No real solutions. Again, we'll talk about imaginary down the road, but I'm okay if we just want to say no solution. And then the single solution would be right here. Okay, just one solution. It's a very specific case. X equals, and again, if we're following my advice and saying, hey, set up that positive negative, the square root of 0 is 0. 0 times 0 is 0. But there's no other combination, right? So this would be one. You hopefully have the kind of the sense to look back and say, well, there is no such thing as positive 0 and negative 0. 0 is neither. So that's what it would look like to get just a single solution. X equals 0. All right, let's go through this part D. There's a little bit more going on there in the sense that what the heck's going on? There's this quantity squared. So we are at a point where there's nothing I can do here. So things that we cannot do, you can never, ever, ever, ever do. We would never just drop this in there and make that x squared and 49. That is absolutely wrong, incorrect. That's not how that works. I can't subtract a 7 because obviously we would be ignoring those parentheses and the squared. So I can't do that. We're kind of stuck there unless we say, hey, you know what? I can get rid of this squared on the left side of the equation by square rooting it. Oh, here's that mechanical piece. I'm writing a little symbol of a square root. The first thing I'm going to do is write plus minus. All right, and then let's get everything else where it goes. So this square root and this squared essentially just cancel each other out. They're inverse operations, which we'll come to look at eventually. And then, all right, what happens on the right side? I've already set myself off. I'm not going to make that mistake of forgetting that there's two solutions. The square root of 28. Okay, so I think we're kind of like this now, where that 28 has got a 4 and a 7 in there. Let's take care of this right side first. So there's a square root of 4 times the square root of 7 to get positive negative 2 times the square root of 7. Just don't forget, oh yeah, that's right, x wasn't truly by itself yet. But I think at this point, I say, all right, yeah, I can fix that. How do I get rid of a 7 over here? I would subtract it from both sides. You're almost always going to see it written like this, where I'm going to say, all right, left side, done, x equals. Most of the times we're going to want to stick that little negative 7, instead of subtract 7, it really just means negative 7 in front of the plus minus, and now it almost turns into an operation. Negative 7 plus 2 times the square root of 7, and then negative 7 minus 2 times the square root of 7. So it's not a super pretty answer. It's kind of clunky. There's this negative 7 plus this, negative 7 minus that, but that would definitely be in simplest radical form. If there was a situation where I said, hey, write it as a decimal, that's exactly what I would type on my calculator. Two different things. Negative 7 plus 2 root 7, negative 7 minus 2 root 7. All right. So let's go through a couple just examples, full blown examples. I know those are kind of our examples already, but solve the equation using square roots. Write your answer in simplest radical form would be the directions here. So yeah, kind of traditional. What do I got to get rid of first? I mean, I would think most people want to add 31 to both sides. All right, so left side, I've got 4x squared equals 80. Okay. Here's another spot too. We got to get the x squared by itself. This 4x isn't attached to us forever. Like, we can get rid of that. That's 4 times x squared. So let's divide both sides by 4 first. X squared equals 20. Now we're basically where we were at, that part A in that last one. I'm going to square root both sides. I've square rooted. I drew the little symbol, so I'm going to make sure I set myself up for two solutions. X equals positive negative square root of 20. And then here we go again. There's a square root of 4 times the square root of 5 tucked in there. So I'll just bring it up over here to the right and kind of finalize this. X equals the positive negative 2 times the square root of 5. There are two solutions to that. All right. You know what? I'm going to do another just kind of extended 2A, holy cow, 2A part 2 or whatever, just to make one up here for us, because I know this happens sometimes. And I'll try to keep it simple. Something like x minus 5 squared plus 4 equals 20. All right, so it doesn't look a ton different than that. I guess there's a quantity there, so it's a little bit different. What's the first thing we should do? Let's subtract a 4 from both sides. X minus 5 squared equals 16. All right, we saw this earlier, where let's square root both sides. Let's square root this side over here. Whoops, I square rooted something in solving. I got to set myself up for two solutions. Left side, we said, hey, that's going to cancel that out. I'm going to be left with x minus 5. And then in this case, the reason I chose to do this just kind of made up example on the fly here, there's an equals there, is that, okay, this one was a perfect square. Hopefully we like that, and it's like, all right, sweet, that's kind of a whole number. And so I don't have to mess with that simplest radical form stuff. So it's this positive negative 4. That's where that mechanical plus minus is helpful. I didn't forget that there's two solutions. And just like the last one, let's say here, let's put this plus 5 and say, just let's stick it in front there. 5, it's positive, plus or minus 4. Now this is 1 because of that 4 being another whole number. Let's do these two operations and just say what? x equals, what's 5 plus 4? 9. What's 5 minus 4? 1. Like, forgot what I was doing for a second. 1. So that there's a case, I mean, if it works out that way where you've got nice numbers, let's do those operations. I know on this one, I'll jump back and forth here. But on this one, we left it as -7 plus this just because we couldn't combine those. That's not such a nice number, so we just left it like that. But in a case here where it was 5 plus 4, 5 minus 4, we can do it. All right, so go ahead and evaluate those ones if it's nice and clean like that. All right, a couple other examples, hopefully ones that I don't think this one ends up being too bad. I would subtract a 9 from both sides. Right? It's basically move everything away from the squared value first. So 3x squared equals -9. Divide both sides by 3. Divide by 3 to get x squared equals -3. So here's that situation we looked at. I'm square rooting both sides. Yep, I'm square rooting. But what is the square root of -3? If this is a negative number, yeah, and we're just down to an x squared, this is one that we're going to say no solution. Okay, just be careful. This exact, a similar problem that you might jump too soon to say, whoops. What did I change? Not much. Well, how would I solve this one? I'd subtract a 9 again, so I'm going to be at -3x squared equals -9. Sometimes people see this and say, oh, there's a negative number over there. This is a no solution, forget it. But actually, what would we do? We'd be dividing both sides by -3, and then all of a sudden, x squared equals +3 again. I square root x equals +- square root of 3. So just be careful that you don't too soon say, hey, there's no solution just because there's a negative number over here, right? If it ends up turning back to a positive value, we'd finish the problem. All right, I think we got one more here. Oh, good one. I'm going to slide this actually over just a little bit. Okay, so some fraction involved here. How would I get rid of this 2/5? Again, we can't distribute it. I can't drop in the squared. I'm going to suggest this right here. Let's multiply by the reciprocal on both sides of the equation. Why? Because I got 10 over 10 and those cancel. So that leaves me with x plus 3, the quantity x plus 3 squared, over 5 times, how do you multiply fractions? 5 times 5 is 25. 2 times 1 is 2. So that's what we're equal to. I know that's 12.5. But the problem is, if we're sitting here like this, x plus 3 squared equals 12.5, and I say, all right, sweet, square root both sides, I don't know how many people are going to be able to fix this right here, because we didn't really talk about what decimals underneath a radical. It's just like a fraction basically underneath a radical, like 12.5 is a fraction. So there's no fractions, no decimals really allowed, I guess, if we're going to say it like that, underneath a square root. So this wouldn't be in simplest radical form. So it's like, how do I fix this? We didn't really go over that. This though, so I'm kind of stuck here. I think if I'm doing it that way, 25 over 2 has the exact same value as 12.5, but at least on this one, I think, hopefully based on what we went over, when I go to square root both sides here, left side is definitely x plus 3. And I'm doing my plus minus so I don't forget it, but we've dealt with stuff like this today already, or in these notes. So I can fix this right side, right? So that's one. It's almost like a separate problem. Now let's fix this 25 over 2 underneath this giant radical. So the first thing we would do, we would split it. I'm just kind of working over here to just separate my work a little bit. I get 5 over the square root of 2, so that was kind of a nice numerator for us. I still have that radical downstairs that I say, I got to fix that. We can't leave it like that. I'd multiply both my top and bottom by the square root of 2. Top we smash together. Bottom we know what's going to happen. And I think we're in good shape. 5 and the 4 don't reduce. Oops. No, I screwed up. 5 and 2. Ooh, I'm glad I caught that. The square root of 4, which is 2. So now if I come back over, here's where we're sitting. The positive negative 5 times the square root of 2 over 2. All right, so that's what this turned into. You can see my work over here. The last part would be, just like any of these other ones, bring that over. And because of the way this is, we're definitely not going to be able to combine these. So I would say my final simplified, simplest radical form solution would be -3 plus or minus 5 times the square root of 2 over 2. How's that for a simplest radical form answer? Yikes, big old fraction. Some square roots in it, 3 plus or minus, -3 plus or minus. So there we have it. That one's a beast. But I guess the big simplified note here on that was, when at all possible, we want to try to stay with fractions versus decimals, which I know is counterintuitive for a lot of us. We don't like fractions, but again, here's kind of the example of why. Like we wouldn't be able to finish this right here. All right, so let's check our stuff here. We've definitely solved quadratics using square roots. I think we can cross that off. I think the next one we're going to look at here is the real life problems. It's a good chance for it. I got the notes set up that way, and hopefully it's a nice break. This is a long note session, obviously, so whatever. Just stay with it. Modeling a dropped object. So this is not something we have to memorize. We'll see throughout the course of the chapter here that there's a couple different formulas, kind of physics, where you would normally kind of typically see something like this. Formulas that we'll use in a variety of ways. So basically this model, h equals -16t squared plus h sub 0, it's a little subscript there, is for modeling a dropped object. So we're standing there, I got a ball in my hand and I just drop it. This accounts for air resistance, or assumes that air resistance is negligible. This is like a constant, a gravitational constant, I believe. The big things that we need to kind of know for this, what does this stuff stand for? So T is definitely time in seconds. Okay, so the T is time, and that H with the little 0 is your initial height. How high are you dropping your object from? Are you on top of the roof? Or are you just standing? So your initial height in feet, we should say. What are the units there? So the seconds on time, feet on your initial height, and then the H is the current height, or the height after height in feet again after T seconds. So kind of think of it as like the height in question, or the current height, after we've dropped this object for X amount of seconds, or T amount of seconds. All right, so it's not a super fancy one. I'm just trying to give us something that we can, we get so caught up sometimes in the skills, like how do I solve? Where might we see a need to actually use some of these skills? So I kind of like the example here where science competition students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. So it's basically, hey, we're dropping something from 50 feet. I think in my formula, if I just re-sketch it here or just rewrite it, -16t squared plus h sub 0. That 50 is going to be our initial height. So for part A, when it says write a function that gives the height h after t seconds, all that's asking us to do, don't read more into it than it is. It's telling us we want to leave. It's a model. It's a function. We want to leave h generic. The -16 is always -16. The t seconds is generic as well. The only thing that we're really customizing for part A here is the initial height. All right, so we said we're dropping something from 50 feet. That's this part. Write a function that gives the height h in feet of the container after t seconds. That's our model. Okay, so that's all I had to do was I'm just checking to see, do we know where what the h sub 0 stands for? What does it mean? Plug in your 50. So I've done this first part of it. Write a function that gives the height. That's done. So that was easy. It was just kind of putting the 50 in there for the initial height. There's another part. Now it says basically use that model. How long does the container take to hit the ground? So what are we actually solving for? How long? We're talking time here, right? Seconds. So the t is the unknown. I must know the h then. All right. That's hopefully how we would interpret that. If we're solving for t, we must know the height. So when we hit the ground, what would be the height in question, or what is the current height of an object on the ground? And hopefully we see that and think 0. What the height off the ground would be 0 if we're on the ground. So the second part of A here involves, all right, let's use some of those skills that we were just working on and solve this equation for t. Most of the times, it doesn't say it in the directions here, but it's very common for a word problem. We'd want to be rounding. Usually, we don't want necessarily simplest radical form. So I'm totally fine with us solving this one here. Still using traditional methods. I'd subtract a 50 from both sides. So negative 50 equals negative 16 t squared. We'll divide both sides by negative 16. Negative 16. I'm just going to come over here. That's not a terrible number. So let's save our rounding till the very end. 50 divided by 16 is 3.125 on the left side, and now we're equal to t squared. So I've kind of gone through some of those same things we were just working on the other examples. I'm down to t squared equals this. So we all know that, hey, at this point, we're ready to square root both sides of the equation, and I'm going to get t equals. We'll set it up for now as plus minus, just like we did on all our other ones. So it's the square root of 3.125. My calculator is saying 1.7677666953. So here's the point where, okay, let's round this maybe 1.77 seconds. And I do want to, like, what's with this plus minus here? Do we need both of those? And the answer would be no, right? How long did it take this object to hit the ground? I don't know. I don't think it makes any sense to say it took negative 1.77 seconds. So a couple different things going on here with a word problem. We want to make sure our answer makes sense in this, that we're talking positive seconds, and it's okay to have a rounded answer here. So about one little over or just short of 2 seconds it takes this object to hit the ground. All right. For our part B, is kind of the other way we might use our formula. When I see this, I think for most people it's an interpretation of that right there. What does that mean? Find and interpret h of 1, h minus h of 1.5. What is that actually saying? So that's saying that, I guess this first part, what does h sub 1 mean? Or not sub 1, but h of 1. That means, what is the height after 1 second? So it's different. It's not saying we're 1 feet above the ground or 1 foot above the ground. It's the height after 1 second. And now that we know that okay, then this then would be the height after 1.5 seconds. So that's the interpretation there. I guess, if I wanted to make my model even, more accurate, although what we had was fine, we could write this as h of t, because then it incorporates, hey, that's the height after t seconds. So maybe that helps to kind of say, oh, okay, that's where that's coming from. The height after t seconds, the height after 1 second, the height after 1.5 seconds. What's the height after 2 seconds? There is no height, right? Because we said it's going to take 1.77 seconds. So what we would be doing here, I'm tight on space. I would be plugging in a 1 here and evaluating. What do I get? What's negative 16? So I know you can't see me, but I'm typing this in my calculator. Negative 16 times 1 to the second power. I probably don't even need a calculator here. Plus 50, because it's just going to be 50 minus 16, which is, so h sub 1, or h of 1, I keep saying sub, equals, what did I say, 34 feet, exactly 34 feet. H of 1.5, so I'm repeating that exact same process, negative 16 times 1.5 squared plus 50. Still not a terrible number, actually. I got 14. So those, after 1 second, we're 34 feet off the ground. After 1.5 seconds, we're 14 feet above the ground. The last part is, well, I guess I didn't interpret the full thing. When I subtract these two numbers, what does that actually mean? 34 minus 14 is 20. So I guess the last thing is, what is the interpretation of that? This, what do we drop? An egg falls 20 feet in half a second there, from 1 to 1.5 seconds. So we would say something like the fall of 20 feet from 1 second to 1.5 seconds. So it took a half second to fall 20 feet during that time interval. All right. So that's kind of what we would be doing there. That's basically the one example we'd look at is kind of a real life or a word type of problem from this section. Okay. Using this formula, just a couple different ways. Maybe you solve for the t where we put the object on the ground, or maybe plugging in t values and finding it, something along those lines. All right. Whew, we're still going. Holy cow. I think we can take this one off there, solve real life problems. The last thing we got to look at, factoring. Okay. So in class, we broke this into 2 days. That's about where we stopped after day one. Just because factoring, oh my goodness, look at all those slides. We'll go through them as quickly as we can. Obviously, again, I know you're watching the video here, so you can kind of pick and choose the parts you need to watch, but let's go through the factoring examples and we'll be all right. So first thing that goes along with is this zero product property. We added this to our notes. The big takeaway, and I think it's something that everybody knows, that if I multiply two things, A times B, and get 0, what has to be true? Either A is 0 or B is 0. That's something you learned a long time ago in a previous math class, right? Something times something getting 0. Well, there's no way around that one of those values have to be equal to 0. Okay. For us, where does that come up? Why are we talking about that? It seems like such a basic concept. If I'm multiplying still, right, this is multiplication in between there. If I'm multiplying two quantities and getting equal to 0, then either this quantity has to have a total value of 0, or this quantity has to equal 0. Okay. So where we're going to see this is, these quantities might look like this. So I'm multiplying these two quantities together and I'm getting 0. That means that either x plus 3 has to equal 0, or 2x minus 1, that whole thing has to equal 0. Well, one of these is easy to answer. I think the one I've got on the left here, if I subtracted a 3 from both sides, x equals -3. Most of us could probably look at this and say, yeah, -3. That's the value that would make that 0. This one's not as obvious, so that's why I think it's helpful to kind of write it out like this, that, all right, if I add a 1 to both sides and divide by 2, that's my other potential solution to that, okay? So that's kind of what's behind what we're doing when we're about to do some factoring here. Most of the time, we're putting stuff in this form. That's the process of factoring, is putting something in this form, so we can finish relatively, hopefully easy, by doing something like this and saying, oh, I either got to make this 0 or make this 0. Okay, so that's kind of the basis of what factoring is. And essentially, so here's our factoring notes. I think there's room here for this. That's what we're doing. We're going from, let's write this out here actually, from standard form, ax squared plus bx plus c, to should probably put an equals 0 there. We're going from standard form to intercept form. We kind of just talked about that this gives us hopefully a relatively easy finish. Okay, so that's kind of the big picture of what we're doing. These are just some general guidelines when we're factoring. we'll talk about what does it mean to factor out a common term, but that's usually what we want to look for first. Is it possible to make the term smaller by factoring out a common factor? We'll talk about this pattern. There'll be other ones that come up in future lessons, but for right now, hopefully we'll be able to recognize the difference of squares pattern, and then we'll look at factoring when my a value is 1 versus when my a value is something other than 1. So that's what we got to get through. There's 4 examples. We're basically going to do factoring out example, a difference of squares pattern, and then one of each of these 2 right here. Okay, so let's just jump in and go. The nice part is some of them these kind of go quick. So if you're looking where does this end, there's not a whole ton left. Okay. All right. Just like the graphing, I want to be equal to 0. We said that was part of this. I mentioned it, but we need to be equal to 0. If we're going to solve this equation, I can't have this be another number over here. So we got to be equal to 0 when we're factoring. This is nice. It's set up to be equal to 0. I see this as factor out. So the first thing I want to look for is there a common value or a common term that I could take, that I could kind of divide out of both of these. So I see the 11 and the 44, and I see that, yeah, those both divide evenly by 11, and they actually both have an x term, so I could divide that out as well. So when I say divide out or factor out, it's kind of like undistribute, reverse distribute a number. So we said we could take an 11 out of each one of these, and I could take an x out. So I'm kind of pulling out. Usually when we're distributing, we're going the other way, where we're dropping something in this way. But when we're undistributing or factoring out, we're actually taking something out. So if I divide out, if I take out an 11x from this first term, what has to be there still? There's always going to be something there. In this case, there's an x. So if I were to redistribute the 11x, sure, it would be at 11x squared. I took a lot of this second one out, but there's still something there. I didn't take the whole thing. And the quick check is 11x times 4. Yeah, that's 44x. So that's a distribute out. Just so we can maybe see it while it's coming up here. I know this is going to happen. It's going to confuse people sometimes. If I have, let's do something like 2x squared minus 2 even. And I say, hey, factor out of that. Oops, got to be an x there. Well, it doesn't have to be, but and I say, hey, factor out of that. And you say, okay, sweet. I can factor out a 2x out of both of those. There's going to be an x here. I took this whole thing, so there's nothing left over here, right? No, we didn't subtract it. We actually divided it out. So if I take the whole term, there would still be a 1 value there that I got to hold for it. Okay, so I just wanted to mention that. That's not part of this problem, but just if we take the whole thing, if we take the whole term out, we still need to leave a 1 there to hold that place value. All right, so the finish then, we're at this spot where we kind of talked about that 0 product property. You don't have to, like, this would be factored, but if we were using it to solve, we kind of want to think about this as I'm multiplying 2 things together and I'm getting 0. So I either need to make 11x equal to 0, or I need to make x minus 4 equal to 0. So how do you solve this first one? You divide both sides by 11. Oh, x equals 0. How do I solve this second one? I'd add 4 to both sides. X equals 4. So that's our 2 solutions. So I know the process is different, but just like everything else that we've done in these notes, a lot of cases we're ending up with 2 solutions. 0 and 4. There's still the potential for a 1 solution. Most of the time with factoring, most of the time we'll end up with 2, and they should probably be relatively clean solutions, no square roots. All right. So that's the general process. We just got to kind of look at some of the different things that come up. So that's a factor out example. Let's look here. Next one. So it'll eventually be our difference of squares pattern, but it starts kind of like the last one. I mean, let's talk similarities, differences. I think hopefully we're recognizing that there's a 2 and a 128. Those are both even numbers. So I can divide these both by 2. I can kind of factor out a 2, but the difference is that last one would have had an x right here if this was just like the last example. This one doesn't have that. So the most I can take out, so it's kind of a different situation that I can definitely take out, and I want to take out that 2, but that x squared is still there, and I've still got a 64 here. So I'm multiplying 2 things and getting 0. But the problem is, this one, there's no place to input an x value. So I still see a squared here. I want to break this up. So this is what's called, if we just maybe focus on this part of it, the x squared minus 64. This is called difference, and I know it was earlier, difference of squares. Why? Because it's literally the difference, right? Subtraction means difference of two perfect squares. X squared is a perfect square. 64 is a perfect square. So it's pattern based. This factors, and for right now, that just take my word for it, that this factors, what's the square root of x squared? X. What's the square root of 64? 8. Okay. It'll have to work out, though, where there's a positive negative there, or a plus minus. And the check, if you don't believe me, is, or maybe the verification, the confirmation, would be if I took x plus 8 and multiplied it by x minus 8, what's going to happen? I'd multiply these terms and get an x squared. I'd multiply these terms and get a negative 8x. I'd multiply right here and get a positive 8x. And I'd multiply right here and get a negative 64. And we would simplify and say, hey, negative 8x plus 8x is 0. So we end up with x squared minus 64. So it puts us right back where we started. That's kind of with factoring how it works. We're basically unpacking something like this in standard form and putting it into its factored or intercept form. All right, so that's kind of the why behind it, the difference of squares pattern. So hopefully we see it, we recognize it. It won't take more than just hopefully a few examples just to say like, hey, okay, I know how that factors. X plus 8, x minus 8 equals 0. So then, now we're technically multiplying three things together and getting 0. I can't make this one equal to 0, so that 2 is just kind of along for the ride. But I ask myself, how do I make this equal to 0? Or how do I make this equal to 0? And we say, oh, x equals negative 8. Whoops, negative 8. Or x equals positive 8. All right. Couple more. We're getting there. We're cruising. Let's look at this one. So now this is that I would kind of call this traditional factoring, where I've got something that we'll put in standard form here eventually. So let's just kind of get into it. X squared. The first thing I'm gonna do is get this 45 to the other side. So minus 4x minus 45, because we said we want to be equal to 0, and ultimately we're multiplying and getting 0. So this is definitely just the first one we're looking at where it's true standard form. Ax squared plus bx plus c. How do I unpack this? How do I go from this form to intercept form? So it's kind of like this, where it's like, I want to, I'm looking for a combination of numbers that I could multiply and add to get this 45 and this 4. So here's how I kind of teach it, that I would say we're looking for two numbers. I need two numbers that ultimately multiply to negative 45, use the negative, and those same two numbers should add up to negative 4. So I give myself a little bit of like just something to look at where I can see, all right, I need two numbers that multiply to C right here, right? This is my C term. I need two numbers that multiply to C that add up to B. It's got to be identical, the same two numbers. So when I see 45, the first ones I think of are 9 and 5. So I'm kind of just ignoring the minus for a second and just saying, okay, 9 times 5 is 45. And the difference between 9 and 5 is 4. So I think, I can make this work. I just might have to play with the signs a little bit. So if I make the 9 negative 9 times 5 is negative 45. I have to do it here too. Does that add up to negative 4? And it does. So I say, okay, cool. That's my combination of numbers that I'm looking for. Once I know these two numbers, we're ready to unpack this. I'm just going to bring it over so a little bit. That it's going to factor into two binomials, okay, equal to 0, where it's x squared, the square root of that first term again is going here and here. And then I just use the signs of these. So I said it was negative 9. So I'm going to write a negative 9 right there. And I'm going to write, this is a positive 5. So I'm going to write that as positive 5. You can double check it. I'm not saying you have to. I definitely wouldn't. But if you just want to confirm, like, hey, did I factor that right? You'd remultiply this and this to see, like, okay, what's going to happen? We're going to get an x squared. We're going to get a 5x. we're going to get a negative 9x, and then we're going to get a negative 45. And this time when I put these two together, I end up right back where I started, right here. So that's kind of all we're doing is you're trying to come up with, and there's different ways. Sometimes people guess and check and do it that way. I like this because it gives me a little bit more like just direction. Just finish the problem. So how do I make this part equal to 0? X would have to equal 9. And you can just, comma or whatever. Or I could make this equal to 0, this part right here, and say x could also equal negative 5. All right, that wasn't bad. Like that's a decent, you're kind of using some of your mental math skills there. 9 times 5, 45. And some people kind of like doing that because the numbers aren't big and you're looking for those combinations. All right, here we go. Last one. Now this one it's similar, but it's different. It's one of those ones that there's some stuff that kind of feels the same, but then some that some that don't. So let's start it the same way. Let's get this at least equal to 0 plus 3. The signs are important. It makes such a difference. If I wrote that as negative 3, this is going to be messed up and it's not going to work. So how do we start this one? I kind of want to have some sort of approach. I see let me write it down here and say, okay, here's where I need two numbers that multiply to 12 that add up to negative 13. So I'm trying to keep it similar to that last process. So the first thing why am I doing this? Where'd that 12 come from? The first thing I'm looking at is, oh, darn it, I can't factor this the same way as the last one because of this 4 right here. The last one had a 1 for that leading coefficient, that a value. When this value is 1, we do this process, the one that we just went through. When that number is anything other than 1, 4 in this case, I need a little bit of a change up. Okay, so we'd look at using the same process. I need two numbers that multiply to a times c. So here's my a value. This is the 4. The c value is 3. So I'm doing a times c, 4 times 3. That's where this 12 came from. The b value part actually stays the same. Like the adding one. It is still just b. So let's see if we can come up with those. Let's see, 6 times 2, no. 4 times 3, no, that only adds up to 7. I think the combination we're going to have to use is 12 and 1. So again, I'm trying to just treat it like positive right now. So 12 times 1 is 12. 12 plus 1 is 13, and we got to figure out how can we make this work. And sometimes, you could potentially run into something that doesn't work out nicely. You say, okay, hey, this one doesn't factor. This one does. Negative 12 times negative 1 is positive. Negative 12 plus negative 1 is negative 13. So I like our numbers. Here's another big difference now. I can't just finish this one like the last one and say, oh, that was easy. X minus 12 and X minus 1. Yep, that was easy. Because why? Why can't I do that? Because if I try to re-multiply this back out, what's going to happen? I'm going to get negative x, I'm going to get negative 12, and then I'm going to get a positive negative 12x, and then a positive 12 for the last part of it. I know I'm running out of space there. But when I go to combine all this stuff, I get negative x minus negative 12 is negative 13x plus 12. That's not what we wanted. Right? This is not the same as this. Okay, so I like our combination, this negative 12 and this negative 1. For sure, we didn't make a mistake, but there's something that's got to happen in between here. Okay, so here's what I do. I take these two numbers, this negative 12 and this negative 1, and I essentially go back to my original problem and start writing it again. So I'm starting with this 4x squared, but instead of writing this as negative 13, we just break that negative 13x into our numbers that we came up with. So negative 12x and negative 1x. All right, so I've broken that 13 up into negative 12 and negative 1. And then I still bring the c value just as it is. Okay, I know this is kind of a process and it's going to take practice to do it. But just over time, I've kind of found this to be the people have had the most success with this one. Okay. All right. So hopefully you're with me up to this point. From here, I'm going to need to. to group these first two terms together. So put parentheses around these first two of all their signs and everything. And for the second two, I'm going to do the same thing. Just make sure I almost lost track of it there. Make sure you don't lose track of any minus signs or operations. So that minus that was in between there now became like a -1. All right. Still with me? So on this first group, I've got 4x squared minus 12x. What I'm going to look to do is what we did on our first factoring example is see how much we can take out of there. Take as much out of that, factor out as much as possible. Okay, so I see the 4 and the 12, and I say, hey, you know what? I can take a 4 out of there, and they both have x's, so I can take an x out. What has to be left here? There has to be an x still, and there has to be just a 3 remaining there. Okay, so kind of the next step is after I group them like we did, I'm going to look at the first group and see how much can I take out of there. What can I get out? And that's where we end up. Now for the second one, for the second group, we're just going to reuse this right here. I'm going to stick that exact same thing right there. Okay, so those should always be identical if we're following this process. I just need to ask myself, how did I get from this to this? Because these aren't identical right now. It's -x plus 3. Now I'm saying it's positive x minus 3. So what had to come out of this to make it look like this? And hopefully the answer, we're all answering with -1. Like -1 had to kind of get undistributed there to leave us this result. Whew. All right, we're almost there actually on this one. The finish is now put this stuff together. The stuff on the outside, the 4x and the -1, gets its own set of parentheses. And then we just use one of these x minus 3s. I'll explain how this works all in a second, but let's at least finish this, okay? So we said take the outside stuff, the stuff that got factored out, and put that together, and just use one of these x minus 3s, and and that's how we end up factored. The last part is at least still the same, so hopefully we're sitting here and we're saying, all right, how do I make 4x minus 1 equal to 0? Or how do I make x minus 3 equal to 0? So the top one is probably the tougher one here. I'd add 1 to both sides and divide by 4. X could equal 1/4, right? I didn't show my work there because I'm just so tight on space, but I added 1 and I divided by 4, 1/4. And then for the bottom one, x would equal 3. All right. Holy cow, that's tough. Just if you're looking for a reason why, or how does that, it just seems kind of random. Why do we just use one of these and group that stuff together? Remember, factoring is, unpacking a standard form. If I was going to remultiply these out, what would happen? I would go 4x times this whole thing. So I would go 4x times x, and then 4x minus 3, but I'd do a 4x times that. So 4x times x minus 3. And then I would also have to multiply -1 times this whole thing. So you can kind of see, if I'm reverse engineering it there, that's where this step right here came from. How did we get there? Well, we broke up that number strategically. So obviously at this point, I'd be kind of, I'd be distributing this back in there. I'd be multiplying that back in there. So it's, without finishing the full thing reverse there, that's kind of the why behind it working that way. But we'll do one more just to make sure that we see it a second time here, but that's where we'd end up, okay? All right, going on to we're well into these notes here. Last one. So just one concept here, add to your notebook. When we see the 0 of a function, all right, everything we've been doing is what? Solving these factor ones, we want to make sure that we're equal to 0. Equals 0. If equals 0, if it wasn't equal to 0, we manually kind of move the number over and set it equal to 0. So this is more just a generic, when we're talking about the 0 of a function is the x value that makes it equal to 0. So I guess the long story short, when we find this, a direction that says find the zeros of this function, like the next one's going to say find the zeros of the quadratic function. It's kind of a semantic thing a little bit, where it's just, we're talking about a generic function here where these were equations set equal to 0. I guess long story short is when we find the zeros, we have to just manually set something equal to 0. Okay. So for like us doing this, like finish that in your notes. The zero of a function is essentially just another. It's kind of a fancier name for a solution or a root almost. They're not quite directly interchangeable. Solution versus root versus zero. For our purposes, that's how we should think of them though. Is find the zeros means find the solutions. Okay. So last one, I promise. Last example of the notes here. Find the zeros of this quadratic function. So when I see that, all I'm doing, I'll rewrite it, I guess, but I just need to manually set this equal to 0. Like that's the one thing that we have to do to start the problem. You say, okay, sweet, I can do that. Find the zeros, set it equal to 0. Find the zeros. Oh man, how do I do it? This is another one of those tougher level factoring, the one that we just finished. So let's go through and do it. Let's go through that process, hopefully a little quicker. How do I start? All right. I would look to factor out. I see the 2 and the 12, but unfortunately this 11 doesn't allow me to factor anything out. So I think we're already here. Let's find two numbers that multiply to 24. Remember, 2 times 12, that's where that 24 is coming from. So I need two numbers that multiply to 24 that add up to negative 11. And 24's got some factors. 6 times 4 is the first one I think of, but 6 plus 4 is 10. It's not quite there. 12 and 2, no, not going to, well, 12 and 2 is close. You know, the difference is 10 or 14. How about 8 and 3? 8 times 3 is 24. So that's, again, why I think it's nice to have just this process of being able to see the numbers. Some people just kind of don't write these down, and they sit here forever and they don't really have a game plan. At least this gets us kind of moving. All right, 8 and 3. Can I make that work with the signs and everything? What if they're both negative? 8 times negative 3, yes, is absolutely positive 24, and then negative 8 plus negative 3 is definitely negative 11. So yeah, I think I got my combination. Remember then, though, the next step is, we'll just keep this 0 following us the whole time. We got to rewrite the original equation, but we're breaking that 11 up into, let's switch it, let's write this as negative 3x and 8 and negative 8x plus 12. The reason I'm switching it, I just wanted you to see it doesn't matter which way I write them. If I kept the 8 first, we would have been able to factor something out, but I just decided, just so we could see it, to see that it doesn't matter, I switched these and said, well, maybe I wrote it as 3 times 8 or negative 3 times negative 8. It doesn't matter how we do it. So I've broken that negative 11 up, and I brought the C value straight down. From here, what did we say? We said we had to group the first two, group the second two. And then out of those first two, we're going to take out as much as possible. Now, in this case, there's not a whole lot we could take out. It should always work out where we're at least able to take out an x, because just of how it's going to work. These first two terms should always have an x squared and an x value with it. So, but other than that, that's all I can take out. This 2 has to stay put, this x has to be here, and then that 3 has to stay. So that's all we could get out. Obviously, if the 8 was up there, if these were flip-flopped, I'd be able to take more. I'd be able to take out a 2 out of each one. But let's see what happens then. So we said, all right, we've got an x on the outside, and I've got this 2x minus 3. Just write down this 2x minus 3 again. Okay, as long as we did that correctly and we didn't mess anything up, this should work out. So now I ask myself, what do I have to take out of this equation, or this expression right here, to make it look like this? So I'm kind of seeing the signs are changing again. So I think I'm going to have to take something negative out. And that 8, it looks like it got divided by 4. Okay, do we follow there? And the quick check would just be to ask ourselves, okay, what's negative 4 times 2? It's negative 8x, okay. And then negative 4 times negative 3 is positive 12. Sure, that checks out. So putting them all together, we said take these stuff on the outside, the x and the negative 4, and just stick that together in its own binomial. We just pick, don't write them both, but just use one of these, 2x minus 3, And then don't forget to finish it that this whole thing was equal to 0. So I'm still, other than, I know it says find the zeros, other than just manually setting it equal to 0, I'm still finishing it the exact same way we did the last one. So I'll do it in the same spot. X minus 4 needs to equal 0, or 2x minus 3 has to equal 0. How do I do that? Well, this first one up here would definitely be 4. 4 minus 4 is 0. This one right here, the bottom one, I'd add 3 to both sides and divide by 2. So I'd get positive 3 over 2. And we can write our answer the same way. X equals 4 or negative, or I'm sorry, or 3 over 2. I am done with that lesson. Holy cow. There it is. Now that's, again, understand that we did that over the course of 2 days, and those are 2 very full days. We're doing it in an hour and a half here that of just straight up notes and hearing Mr. Kroll talk. So I think as we come back now, have we solved by graphing? We already checked it off. We've solved using square roots. We looked at factoring. Yeah, that's done. We looked at the real life solution or the situation. I want to X all that stuff off and say we're done. So there you have it. There is a very long lesson 3.1 solving quadratic equations notes. We are officially done with that one. So thanks for watching. I'll see you in future lessons.